Okay, so everyone should at least know my name by now. I'm Inês Silva. I'm a postdoc at CASUS, which is the Center for Advanced Systems Understanding. I'm one of the few ecologists in there, so it's quite an interesting change from my work before. But yeah, so we'll go over home range estimation. I'll also cover afterwards overlap and meta-analysis, and then some study design. So there is a chance that you ask me a question, and I'll answer at some point later in my presentations. Yeah, so I'll start with just some definitions, some concepts. I'll go over sample size, which there's already been some mentions of sample size, effective and absolute sample size, but I'll go over it again. I think it's important to really understand what that means in this context. The home range estimators, and I'll show you why the other ones are not as good as AKDEs as well. Go through the workflow of home range estimation, and then deal with common biases that people have with their data. Okay, so I think one important thing to consider when we look at space use is that we cannot really separate movement from space use, right? If you are just running through your analysis and you just want that estimate at the end, that number means really little if you don't really understand the biological meaning of that. And a very important concept here is the interplay between the environment, which includes, social context sometimes, the animal's understanding of that environment, the ability to perceive the environment, and any essentially subsequent movement decisions that the animal makes, right? And that's limited by the movement capabilities of the animal. So if you have an animal that can't climb, you cannot consider, that within your space use, right? So as you probably already are very familiar by now, animal movement is autocorrelated. This is a very, very important characteristic of animal movement. So as just an example, this is the elevation of the US. And if we were saying, okay, I don't want to look at autocorrelation within this data set, you would have that figure on the right. And there's no meaning there, right? No one wants to analyze elevation like that. So, and again, one of the very, very important laws of geography is that everything is related to everything else, but near things are more related than distant things. And again, if you ignore this autocorrelation, you're ignoring very valuable information that you get. And if you don't account for that, right, you can undermine inferences, it can lead to overconfidence, because this autocorrelation is informative. Again, if you look at climate change, the fact that there's autocorrelation in temperature is why we want to analyze how the global temperature is shifting a long time. So again, you cannot ignore autocorrelation at any point. Okay, so if animal movement is autocorrelated, it violates any independence assumptions, right? And it's critical if we want to explain animal movement and space use patterns to always incorporate autocorrelation. So even though animal movement is a continuous process, the tracking data that you get, unfortunately, sometimes does not necessarily reflect that. You don't get, exactly where the animal was at any single point in time. There's always some separation, some interval between your locations. So whatever our data, the data that we use is never really a perfect reflection of the real world, right? It's always an approximation. And again, if you have either collected by humans, like with VHF, someone goes out in the field, or collected by the devices, there's always going to be associated errors, the guesstimation sometimes of where the animal could be, precision errors in terms of the location. So, animal movement, continuous time process. There's lots of information when we go to animal tracking data, which is discrete. And the way to kind of interpret this is through movement models, which Chris already started covering a little bit. Obviously, we are trying to simplify, an interpretation of the animal movement to actually then do analysis on it, right? We can't say that the animal always follows an exact movement model. It's just an approximation of the generalized process that the animal goes through. So home range was defined first with Burt in 1943 as the area traversed by the individual in its normal activities, food gathering, mating, caring for young. Occasionally ventures outside of the area, perhaps exploratory in nature, should not be considered part of the home range. So this is the original definition of home range. However, it's relatively vague, right? What is a normal activity? What is an occasional venture? How do you quantify, right, this process? So it's not, essentially it lacks an objective way to evaluate and quantify home range. And something to also consider is that home range is different than a territory. You can have an animal that defends its home range completely, so the home range is the territory, but the territory can also be smaller than the home range. So it's two different concepts. So if you're trying to estimate your territory, it's different than estimating your home range. So it's something also to consider when we're looking at this. And also you have to consider what constitutes an exploratory move, right? How do we quantify exploratory move? Obviously, in practice, it's really difficult to determine. It's not like you can ask the animal, are you just going there and you didn't like it and you came back, or did you use it for something that's important? And if you're not observing your animal, if you're not following your animal and know exactly what it did, and you're just looking at points in a map, it's not like you know exactly sometimes what the behavior was at that point. So typically what we do is just we exclude infrequent outlying locations. So locations that are unlikely to be revisited, and that's how we exclude them. And something also that I think it was covered a little bit in the previous days is this difference between range distribution and occurrence distribution. So there's a lot, if you search for papers on home range that still use the concept of utilization distribution, and they don't really separate between range methods and occurrence methods, right? So it's something to consider if you're looking at older papers, because this is a relatively new distinction. And we have a paper coming out, I'm not sure exactly when, but soon, hopefully, that will go over this in a lot of detail and actually explain this is what range distribution is, this is what occurrence distribution is. But in general, if you're looking at range distribution methods, if you want to actually estimate the range, you are extrapolating space use into the future. This is a very important concept of the range distribution, right? It's not just what you're observing during the sampling period, it's to the future, the likelihood that the animal will keep using that area. So how much space does the animal need long term? The occurrence distribution, however, is you're interpolating between points, right? You're not saying anything about the future locations. You're just saying between these points that I have, what was where did it go? Well, how did it move to that area? So it essentially lends itself to two different types of questions, right? So the range distribution is the home range question, like how big is the area that the animal needs. You can look at population. You can look at protected areas sufficiently large to actually maintain that population that exists there. While occurrence distributions, you're looking at where did an animal cross a linear feature. This is, for example, a road or any sort of linear feature that you want to consider. How likely it is that it visited a location of interest, and how much time did it spend in a specific habitat. These are all questions that you can't really answer with range. So this is something that if you're thinking about this is what I want to do from my research, you also need to know, okay, is the method required range or occurrence distribution? So we have some code that we can go over just to see the difference visually, and I think that helps. Okay, let's see. So this should be at the end of Chris code, so it's CTMM1. Should I put it also with white, or is this visually?
White.
Okay. We can start seeing the patterns of everyone's color preferences here. Okay. I think Chrome was a good one, seemed like. Okay, big enough for everyone to see? Okay, so this is following immediately after Chris's code, so hopefully you still have that run and you didn't overwrite anything. But if you didn't, you can always quickly run over it. If someone needs to do that, I can wait a little bit, but doesn't seem like it. Yeah, okay. So we have here the data set, which is the Buffalo that Chris was running through. So it's the same exact data that we're looking at. And the only thing that we're going to do now is fit the Brownian motion movement model to it, right? And it's this part here, basically saying that the position, autocorrelation, velocity correlation go to infinity for both cases. Because if you remember, the Brownian motion diffuses endlessly, it just keeps going, doesn't come back in any sort of way. And then the isotropic is just saying that it's that circular movement instead of preferring certain directions over others. So that's all that's doing there. Okay. And then we ran also the anisotropic, right? Just to see how it looks like, but it's the same setting here of tau equals infinite. Now something to consider here is that typically you cannot compare a non-range models to range models, right? It's just this is why Chris was going over the variogram, which is when you make the decision, is my data sufficient for home range estimation, right? So typically when you compare those models, you're comparing different things. So it doesn't really make sense. But you can compare the models that are range with each other and non-range with each other. So we can see here the result of model selection between the Brownian motion isotropic and the Brownian motion anisotropic. So in this case, the anisotropic is the best. So there's some, and you can see here as well, that obviously there's some, the variance is bigger in one direction than the other.
Sorry.
Yeah. The microphone?
I'm sorry, but could you just repeat the differences between the anisotropic model and the non-anisotropic model?
The isotropic and the anisotropic. Yeah? Yeah, it's just about is the animal likely to go in every direction the same way? Or is there some direction that it prefers to go across, right? So instead of being a circular, it's more of an oval shape. Does that make sense? Because again, in the field or in reality, you don't necessarily have a circular home range, right? That's not usually what you would get in the field. You can get that, but it's not necessarily reality.
But so if you have the isotropic model, like the shape of it would be based on your data?
Yeah, it's assuming that the variance is the same in all directions. Okay, so we can now see how this specific fit looks with the variogram. So this is the selected model from before, not the Brownian motion yet. But with the Brownian motion model, you can see that, I mean, maybe it's, I don't think I need to zoom in, but yeah. But you can definitely see the difference here, right? How this fits with what we observe. And this one just says, oh, it just keeps going, right? It's endlessly diffuses which is not what we're seeing with the data. But hey, if you wanted to apply Brownian motion model to this is how you start. You're already failing the assumption. You can, but you shouldn't. So this is the range distribution using the fit, which I believe is the OUF model. So it's just doing the range for comparison purposes. And then we can run the occurrence distribution, right? So we can see how the range distribution looks like and what the occurrence distribution looks like. In this case, this occurrence distribution is using the selected model, the OUF model. So it's the ideal occurrence. But we can also compare it with the previous fit of the Brownian motion to see. We already know that it's not good based on the variogram, but we're just going to look what the actual occurrence distribution looks like once we fit the Brownian bridge. Okay, I'm plotting the three of them side by side by sides. I guess some people have already seen the results. Okay, there we go. Okay. So, very different, right? The first one, this is the I think the name is incorrectly, but it's the range distribution. So make sure that that is the range, not cringe. But yeah, so this is the range distribution. This is the home range, right? Then you have the occurrence, but based on the selected model, the best fit model, the OUF. And then you have the same occurrence, but with the Brownian motion assumption there. So yeah, so you can clearly see that if you ask a question and you get this or you get this, clearly you're looking at different things. You're not looking at the same output. So yeah, just to go over it again, occurrence distribution. You are looking at interpolation. You're looking at, given a certain sampling period, where was my animal? What the movement trajectory was it? The likely one that it was. The range distribution, it's looking into the future, assuming that obviously the animal continues the same behavior that it did before. Where will the animal, like how much will the animal need, like the long-term space use. So we can see the impacts, right, of coarsening the data, so essentially making the sampling frequency more coarse. And we can see how that would look like in terms of these outputs. So that's simply what this is doing, is just removing some of the data points from the original data to kind of approximate a coarser resolution. And then again, plotting it side by side. Okay, so there you have it. This is essentially the difference between, a higher sampling frequency versus a lower sampling frequency, and how the range distribution changes and how the occurrence distribution changes. But again, obviously, there's always going to be some differences with the range. It's accounting, or at least it's sampling independent, so it's a better estimate of the distribution without a lot of changes, but obviously there's some differences there. just based on what data you feed into it. And the occurrence distribution the same. In this case, since we are using the occurrence with the best fit model, it's just a little bit more uncertain where the animal was, so it increased a little bit more comparatively to before. It might not be too obvious from the figure, maybe if I go back. Yeah. So it would be this one, right? So we can see that the blues are slightly wider, so there's more uncertainty in the locations.
Faster each time.
Well, it's less data to run, so yeah, so yeah, more uncertain.
But the range distribution is going to be changing.
Yeah, it maintains. Because again, it's since we are assuming that the animal will go to those places eventually, that's incorporated into the distribution estimation. Yeah, I guess we could keep going until it fully becomes the same, because that's eventually it would happen, which is why sometimes if people before were using, Brownian motion to evaluate their data, sometimes it'd be like, oh, this is the home range. But it's because their resolution is very coarse. So at one point, yeah. I mean, I guess that's similar enough, but it's not very good. Okay, so what happens if we truncate the data, right? Instead of having a longer duration, we shorten it, so it's a shorter duration. So doing the same thing, but just seeing shorter and shorter duration. Okay, so we'll just run it a few times just to see the effects. Oh, I think I'm running with sub, yeah. So don't run it with that first line, because then it will overwrite and do the same thing. Okay, so you see that the range distribution, I mean, it's a little bit different, but it's still similar, while the occurrence distribution now it's not really incorporating all the movement trajectory of the animal. Because again, you're only looking at the sampling period. Yeah. It will also eventually just disappear once we don't have any any data. So does anyone have any questions regarding this distinction? Okay, so I can move on. Hopefully, at least at this point, you are aware enough that if you see a paper out there that claims the Brownian bridge is a home range, you already know that it's not. Okay, so now, obviously, home range, we're only looking at range distribution. So this is the definition we use with CTMM, the definition of home range. So essentially, the area repeatedly used throughout an animal's lifetime for its normal behaviors and activities, and excluding occasional exploratory excursions. And obviously, the home range area can be expected to include future locations. So this idea that we're only looking at a certain, can I do the laser pointer thing? Okay. Yeah, looking only at a certain time frame of the animal, right? I mean, you could potentially be lucky enough to track an animal since birth until death, but you're usually not that lucky. You're only doing part of it. So we want to make sure that we are representing as much of this process as possible, and that we're looking at lifetime requirements, not just sampling period requirements. But obviously, this also implies that the movement process isn't changed, right? So if you have an animal that changes, movement behaviors, it could be a bit more tricky. Okay, so this is just an example of, essentially the implications of not really considering, lifetime requirements. So this is data from king cobra in Thailand, the longest venomous snake in the world. And this is the data collected with VHF for the 1 year exactly. And I don't think you can really see it very well in there, but probably in the slides if you have them. There's a boundary around here that is the protected area. I don't think it really shows in the presentation. But there's essentially a boundary there of the protected area. So if you're not tracking the animal throughout the whole time, let's say that for some reason the device failed after 6 months, or there was no more money for people to go out in the field and collect the data, and you'd only get 6 months of data, you'd assume that the animal always stays within that protected area. So you maybe don't have any idea that there's a potential for human-wildlife conflict regarding this species. And actually for this particular individual, it ended up dying once it went out of the protected area. So yeah, it's important to always consider this. So if we look at the home range, that it includes areas outside of the protected area, then we can actually start actually evaluating the conservation management of the species in the site. But obviously this deterministic, or how you determine, do I have enough data to look at home range, right? That's a very important question that we need to look once we look at our data sets. And hopefully by the end of today, you'll have some idea of how to know how much data is enough. Okay, so just to, again, go over the sample size concept. I know there was some talk yesterday about it, and Chris also mentioned it a little bit, but just to really go over it again and make sure that you guys understand, because the absolute sample size, right, is simply the amount of data you have, the total number of observations. So if you collect 1,000 locations, that's what you get. 1,000 locations is the absolute sample size. So it's dependent on your sampling regime, right? And obviously, you want as many locations as possible for your animals in this sense, right? You want as much duration as possible. So for example, if you attract for 6 months and you do a fix every 20 minutes, you end up with 17,000 locations, and that's the total absolute sample size. However, the amount of information that is available for a home range estimation is not governed simply by the absolute sample size, right? So this is where effective sample size comes in. At a certain point, you just don't have as much information that the absolute sample size would give you. And in the case of effective sample size of area, we are just essentially estimating the number of times the animal crossed its home range. So it's roughly estimated by dividing the sampling duration by the average home range crossing time. So this would give you the effective sample size that you get out of your data. So the home range crossing timescale parameter, it's the same as the position autocorrelation parameter. It's the same thing, the tau p. And essentially, how long does it take for an animal to traverse the linear extent of its home range? So for this case, this is a simulation sampled for 1 day, but the position autocorrelation is also 1 day, so it covers the home range within a day. This is obviously simulated in the field, you're going to have an average. It's not like it's saying like every day the animal goes. It's just an average between doing that. But it's a good way to visualize this effective sample size. So you want as many of these home range crossings as you can get. So if you have an animal that crosses its home range 100 times, that's good. You have a good effective sample size. If it only does that twice or 3 times or 4 times, that's not as ideal because the estimate is not going to be as precise. So this is just so you guys can see the difference between what would be the home range crossing of 1 hour versus 1 day versus 5 days versus 10 days. So obviously, if we increase that home range crossing time, the animal takes a sweet, sweet time going over its home range. But obviously, it would be nicer if they did this, because that means that you don't need as much data. But that's very unlikely that you have an animal that within 1 hour, it's using all of its home range already. Obviously, this parameter varies between species and individuals. But you can estimate it with CTMM and have some idea of the potential home range estimation. And obviously, as it increases, it decreases effective sample size. So it's a good metric to consider if you're trying to evaluate how much data you need for home range estimation. So we have here an example from the Mongolian gazelle. This is an individual that was tracked for over a year, 389 days, which you would initially consider that's pretty good, 1 year of data, right? And this is one fix every 5 hours, so it ends up being around 710 locations that we end up working with. However, this particular species has a home range crossing time of for this individual, for example, 141 days. So it takes this amount of time for it to cross its home range. Or even, obviously, over 1 year of data, you end up with a very, very small effective sample size. So 2.7, right? So this is not very good for home range estimation. We'll look over at what you can do if this happens, because this obviously is a reality for some people. But there are ways to at least increase the precision of the estimate. But at a certain point, you're going to always have high confidence intervals in what you have, right? There's only so much you can do with this sort of data set. You just get a better estimate than before. Yeah.
In case of like elephant as a species, they forage in a particular place, then they move from there to another place for maybe 100 kilometers, and they forage there, again come back to another places, and again reach to the place where they started. So how to estimate home range crossing time?
If an animal stays in one area for a long time and then just does a shift and stays there for a long time and then comes back, so there's essentially two sites. Is that what you're looking at?
Yeah.
Okay. You could potentially, and we can go over that a little bit, but essentially calculate a home range for both and then just average both of them, right? So essentially, if the movement behavior changes between those two states, right, you'd want to do it separately and then average, where we can look at how to do that, right? But obviously, because then you also see in the variogram, that's when you see that essentially a lump, right? The animal, the variogram starts by increasing and then comes back to a smaller location, so it does a little bit of a lump. Obviously, it's not ideal for home range estimation, but there's still ways to figure that out. Yeah, and as long as you have, again, good effective sample sizes, and guarantee that overall there is some range residency, right? The animal doesn't keep going into different places. There are ways to estimate that. Okay, so for independent data, so if we assume independence, the absolute sample size and the effective sample size is the same. So if you run on CTMM the IID model, you'd always get the same effective sample size because it's, again, there's no assumption there for autocorrelation. But for autocorrelated data, the absolute size is always going to be bigger than the effective sample size, and sometimes by orders of magnitude bigger. So you can have, 5,000 locations and then, 100, like the effective sample size of 100. And there's, again, many biases that affect home range estimation, and the smaller the sample size you get, the more it affects it. But again, there is some mitigation measures, some corrections that we can do if that's the case for your data set. So just to go over again the different methods a little bit, obviously the first one, the BMM, is not accurate for home range estimation, but again, you'll see it being used sometimes in certain papers. But this is essentially what happens if you coarsen the data for the different methods, right? So all of them, except potentially the MCP actually decreases a little bit. But they essentially, the estimate increases as you coarsen the data, which is not very good for home range estimation because there's no guarantee that your estimate is stable. So yeah, so the first one definitely do not use for home range estimation. Now the other ones, again, you'll still see plenty of papers coming out that use these methods. And even recommendations for these methods in certain papers. The idea that people usually have is that they're easily interpreted. I don't particularly agree with that, but you'll definitely see it being mentioned. Right, so for example, the minimum convex polygon, which is just, you connect the outer locations. It's essentially just describing the extent of locations of an animal. So not the actual estimation of home range size or space use. It assumes uniform use throughout, and also assumes that locations are independent. So any outlier that you get outside of this would increase the MCP. Some people argue that you should use MCPs if you have very low data, but again, as you know, AKDs can deal with low effective sample sizes, so that's not a good excuse. Okay, so then you have essentially the conventional kernel density estimators. Again, an improvement over MCPs because we are no longer just describing the borders of the home range, but we are looking at probability of use. So essentially the goal here is to take a finite sample of data, and then we can make inferences about the underlying distribution of the data sets by drawing these three-dimensional kernels, hills, over each location. And the shape and width of this kernel, which is the bandwidth, the age value, can be selected using algorithms. So you'll see sometimes people saying a KDE with href algorithm or LCV algorithm or other ones that exist plugin. So that's just essentially the way to calculate that kernel and how wide we want to consider it. So then you just average that and you get an estimation of the underlying distribution. So that's just the baseline information for the kernel density estimators. So obviously, as you can see, the choice that you take when you select this bandwidth makes a very big difference in the estimate that you end up with. So we can see here, as we increase this bandwidth, the animal is, okay, we start with, okay, the animal only goes to those locations. There's not even very much connectivity between points, which is obviously not realistic. So let's increase it more and more until maybe the animal was everywhere and I just don't know anything about what's going on. Which, I mean, as you can see, it's not ideal. Any scenario of that is not ideal that we consider. And you'll also see sometimes this selection of the bandwidth be by hand. Essentially, you look at the data and you get an idea of how far the animal is likely to go between the points. I mean, that's not based on anything, so it's very subjective in how you decide that bandwidth. You can say 5 meters or 50 meters or 500 meters, and no one can really tell you anything because there's no baseline that you're going through. So this is the kernel density estimator with the href, the Gaussian reference function, which is very commonly used in certain papers. Again, same as MCP, assumes locations are independent. But obviously, this href tends to change as you have different data sets. So this is going to keep changing depending on what you feed into it. So it's not very stable, right? Because again, the way it calculates the bandwidth is going to change. And it's specific. We have the least square cross-validation. Again, another one that's commonly used. Some papers out there even suggest that this is the best available method to calculate age value, because the one before, the Gaussian reference function, oversmooths, so goes too far from the locations. And this one tightly conforms with the data. I mean, you can barely even see it from here, but it's basically saying my trajectory is my home range. And this gets worse and worse the more data you have. And again, it still doesn't account for any sort of temporal structure of the data. So are these methods really describing home range is the question, right? And as Chris also showed, like what happens if you thin the data, so right? You have a data set, you want to apply a KDE, a conventional KDE, following the assumption that the locations are independent. So you thin your data until you achieve independence, right? So you start with this really nice data set with over 2,000 locations. You thin it until you achieve independence, so you end up with 30. So we already lost 70% of your data. And then you plop a KDE on it. So obviously, you can see that it does still have an influence in how it looks like from the original data to the thin data. And again, the age value changes between the two because, again, it's the calculation of this Gaussian reference function. So you spent all this time in the field collecting all these nice little data sets, and then you end up with this. I mean, at that point, you might as well just go once a day to your location and get the point, if that would be your end goal, to just do a conventional KDE. But that's not what we want, right? We want good information. We want to use what's available and get a good estimate. So this is not a good way to proceed with your data set. Yeah, and how confident are we in these estimates anyway? Because it doesn't give you any confidence intervals. So you don't know how confident you even are that this is the actual home range. So this is basically how KDE, so the conventional KDE estimates the home range as we increase the mass of the tracked animal. So as you can see, as we track bigger and bigger animals, both the accuracy of the home range decreases, and this is essentially the truth, right? The ideal home range accuracy. So it keeps decreasing and decreasing as we have bigger and bigger animals, and the same thing with the number of relocations included. So this is essentially looking at dividing the data sets by half and using the second half to see is the home range including that second half. So the future use of that area. So it also decreases as we have bigger and bigger animals being tracked if we use the conventional kernel density estimator. So this has implications for any big evaluation of home range, any sort of meta-analysis that people do, because we are underestimating the home range for these big animals. Likely because, again, the home range crossing time is likely higher as you go along this gradient. So if you make some conclusions about, elephants or bears, and you're using conventional methods, you are introducing a bias that is not easily resolved. Sorry. That's why you're here. Okay, so we have these previous methods that are assuming discrete time, assuming independent locations, are scale dependent, so the sampling affects the estimate that you keep getting. But in the field, there's always irregularity in time. Sometimes the sampling schedules differ. Sometimes you lose animals. Sometimes you lose devices. Sometimes the GPS device fails and doesn't send a location when you want it to send a location. Again, you never have a perfect data set to work with. So this is where, continuous time movement models come in, and how we can actually evaluate home range estimation in a way that's like you can compare across individuals, across species, across regions. Okay, so we'll Chris already went over this first step of the workflow, essentially identifying if my data set has a range residency, if my animal is staying within the same area, and I can do then a home range estimation, and also went over the movement models and how to select the best fit movement model. I'll go over it again, not as much detail, but I think it's important to really understand this process well, and then go over exactly how to estimate the home range, and then the mitigation measures that we can apply to common biases in the data. Okay, so again, you only are going to use home range estimation with animals that are resident. So if they have animals that are migratory or are essentially nomadic, so don't follow any temporal or spatial patterns, you can't really do home range analysis. You have to look at other stuff. It would be nice, but you can't. So only range residency animals you can evaluate with this method. Yes?
Does this, what you just said, does that also apply to animals which show DL migrations, daily migrations between a night sort of, somewhere where they sleep?
It depends on the movement behavior of the animal, if it stays the same or not, right? Because again, this method assumes that the movement process underneath is the same, and the animal is continuously doing the same movement behavior. If you have cases where the animal is changing very drastically in what it's doing, it might not be ideal to use a home range estimator to evaluate that.
Can I grab the mic? Thanks. But I mean, really, the amount which we're violating that assumption is really a matter of degree and not categorical, right? So I was just looking at some of my data, and for the summer the animal is resident on its range, but it's breeding, right? So it's returning to a nest site or a den site or whatever, and
Yes.
even range resident species are going to have these changes in underlying
Yeah,
movement
exactly.
patterns.
I mean, it's an animal.
Yeah.
It has different behaviors, yes, but it's more the underlying structure of the movement process that we are considering here, right? Obviously, the animal is not always going to be doing exactly the same thing. That's kind of how animals work, but it's more of like over time, like we're looking at a long-term process here. And over time, it tends to, again, if it comes back to the same places, right, it's still having an area that it utilizes more frequently. The main difference here is that we're looking at, purely like an animal that really like migrates in a way that really changes that assumption of the underlying movement being the same. And if you have a nomadic animal that just never really prefers to stay in an area, also it fails that assumption. I mean, there's definitely cases where you look at the data sets and it's not super clear if the animal is, is staying in the same area the whole time. Sometimes that's basically because you didn't track it for long enough, and if you did, you would see that stabilization. But yeah, it's not as straightforward. Okay, so the variogram that, again, Chris already went into it with a lot of detail, and you should know this already. Essentially the way we visualize autocorrelation in the data, right? So we have the time lags between essentially every single location, and it just looks at that. So the more similar the pair of locations, the lower the semi-variance is going to be. So the general idea is that if it starts curving and then it reaches an asymptote is when it becomes uncorrelated, right? When the distance at which there's no evidence of spatial dependency. And if you have before that and it's still increasing, that's correlated data. So if you have something that keeps going, like the Brownian motion, it means that all of it is correlated. It never really reaches an asymptote. The animal will keep going further and further. The lag between the locations is going to keep increasing and increasing and increasing. So we can see here, as more and more data is included, that variogram reaches that asymptote. So you could be, like you're saying, in that case, maybe you just didn't track your animal for long enough, and you're still seeing some increase in the location. But if you keep tracking the animal, you'll see that it stabilizes, if it has had that range residency throughout. So sometimes with the earlier data sets, if you're still only tracking for a shorter duration than is needed, you'll still see that slight increase. So it doesn't necessarily mean that your animal is not range resident. It's just that particular data set is not enough to determine that. Okay, so the conventional models that we talked about before, they essentially get the tracking data and estimate the home range from that, assuming independent locations. The CTMM package gets that data, fits a movement model to it. Essentially, what movement model explains that particular data set that we're working at, and then is going to feed that into the estimation of the home range. So we have all the different models that are used within CTMM. The good thing about CTMM as well is that a new model shows up that is better at explaining a certain animal movement. We can include it and keep improving the model selection part of this. So again, we have the independent data, essentially assuming that all points are independent. This is the same as rolling a dice and getting a number every time you roll. The rolls are independent from each other. There's no dependency, either spatial or temporal, for your data. So it would look like this. You would see a straight line going up and then reaches an asymptote, because again, it does assume that there's a restricted home range. But yeah, so if you see this in your variogram, that means that you have independent data. But as you saw before, that's very, very unlikely that you'll see this this process. I mean, it could happen if you have a very, very coarse data set. Regarding the Brownian motion, again, an animal that's endlessly diffuses, just keeps going. So as time goes on, the animal is further and further away from its starting location. It just basically does not depend on its past at all. And that one, if you look at the variogram, you would see that, again, that straight line going up. So if you see this, it's because your data set is following this Brownian motion model. Then you have all the different modifications of the Brownian motion model, the Ornstein-Ummelbeck, the integrated OU, the OU with foraging that Chris talked about. The main differences, and you saw from the animations, is that the OU is like the Brownian motion, but it comes back, so it tends to move back towards the central location. The integrated OU is, again, similar to the Brownian motion, but it does have persistence of motion. So it does have the velocity autocorrelation within it, and the OU with foraging is bounded and with persistence in motion. It's essentially these two added. So the differences that you would look between the different variograms, the OU at like shorter lags would be, again, similar to the BM, just a straight line up. This is short time lag, so if you zoom in on the variogram, you'd see this. But over a longer time frame, you would see it stabilize and reach an asymptote. So there is spatial dependencies because it reaches that restricted area, but there's no velocity autocorrelation for this one. The OU is similar with the BM at longer time frames, so it would still also have that line straight up, keep endlessly diffusing. But at shorter time lags, you would see a velocity autocorrelation, so you'd have that slight curve. And with the OUF, you'd have that slight curve, again, velocity autocorrelation within shorter time lags, and it reaches a asymptote at longer time lags. And this is typically what you get for a lot of animal movement data sets, is this movement process. Okay, so this is just summarizing the same thing, and that's essentially the parameters that we get out of those movement models. So essentially, doesn't assume autocorrelation. Autocorrelation parameters are null. The BM, the autocorrelation parameters go to infinity. The OU, the autocorrelation parameter is just the position. The IOU is position goes to infinity, but you have the velocity autocorrelation, and the OUF has both the position and the velocity autocorrelation. So there's a sentence that I think some people don't necessarily like, but I think it's accurate enough if you think of it the right way, is that all models are wrong. Essentially, they're not reality, right? They're an approximation of reality. But some are very useful, so you can actually do a lot of things with those models. So I think it's a good way to visualize this, is that obviously you could have an animal that doesn't fit 100% any of these movement models, likely because maybe it wasn't described yet, the movement model that your animal is doing. So maybe, hey, you found out a new movement process and you can publish on it. But yeah, but some are very useful in terms of how you analyze the data. Okay, so one of the ways to essentially see what movement model parameters actually are likely to exist or characterize a given tracking data set, right? So what parameters does my data set fit? So one of the ways to get that is from the maximum likelihood. So it's just an estimator that is the standard approach to fitting movement models. So the goal of the maximum likelihood estimation is we select the parameter values that are make the observed data most probable. So we have these points over here that represent our sample. And one of these distributions is the one that represents this sample the best. Does anyone have any guesses of which one should represent this data? This one? Okay, this one definitely no. This one, maybe the variance is too big, so let's maybe go for one that's, because most of the points are in the center there, right? So essentially the way it's doing the maximum likelihood estimation. Unfortunately, maximum likelihoods does not perform well if you have small sample sizes. For example, we have here 2 data points. So it's like obviously there's a distribution underlying those data points, and that's what the blue line is. But we unfortunately only collected 2 data points in this case. So the ML estimation would say that this is the actual distribution of the points. So if we plotted 2 different data points, it would change and it would change again. So it's not very accurate if we have small sample size. This is just a very simple way to represent the bias, that obviously you don't have 2 data points when you have animal tracking data sets. But this shift in how it estimates the underlying distribution is a problem if you have a small enough sample size. So the idea here is that you could average across the 3 data sets, and the mean would be correct, but then the variance would not be very, very accurate. So a different method that can be better than the maximum likelihood estimation is the residual maximum likelihood. So essentially it trades off the reduced bias in the mean for increased variability. So instead of assuming that I'm very sure that the mean is here, I'm less sure about that, so increase the variance of the distribution. So these are ways we can, again, compare the different movement models. And the reason why I'm going into this is that Chris developed a new essentially estimator to compare the movement models that corrects also these biases that we have here. So we'll see when we go through the code that is one of the options to select this method of estimation. So yeah, so residual maximum likelihood is not always ideal with animal tracking data, because again, you lose variability or you increase variability of the estimates. Okay, so let's go to the actual meat of this presentation, the actual estimation of the home range. So yeah, so instead of using MCPs, instead of using kernel density estimators, the conventional ones, we're using the autocorrelated kernel density estimators, which account for the autocorrelation of the data, which as sampling frequency increases, we know that autocorrelation does too. So we want to make sure we are actually using all the information that is available within our data set. And that's what the AKDE is doing. So we have here an example of a data set that is plotted with the conventional KDE. And this would be the presentation of the, again, conventional home range estimates. And this would be the AKDE with the same data set. So the main thing is that some people would say that this conforms more tightly with the data in comparison to this one that is including areas. Does the animal actually go here? And that would be one of the main criticisms of AKDEs. However, we know that if we simulate data to see following the same movement process, where the animal would likely end up for, so before we had 1 year of data, this is extrapolated to 2 years, so a simulation of 1 extra year of data. We see that the animal keeps using the area and goes to areas that were not included in the original KDE. So you already have a reason to explain why use the KDEs versus conventional KDEs. And we can also see here the comparison between the AKD here on top with the previous methods that we talked about, and also Loco, which I think was mentioned at some points earlier in the AniMove, and how accurate this is at including the relocation. So that same process before of seeing the second half of data and if it's including those relocations in the estimate. And we can see that AKDE is very good at incorporating the relocations. I think you can't even see the variance there because again, it's the confidence intervals are very close to the estimate. But for all other methods, especially if we have low effective sample sizes, they underestimate those locations. So, and we see here the Loco as well if we look at a certain point, even with effective sample sizes of 1,000 locations. it doesn't even get to the right number of inclusions, and even the variance doesn't include that, so it's fully wrong. It doesn't even overlap, so you'd have some idea that the variance would include those points. So yeah, so don't use these methods for home range estimation. We're really trying here to get you guys to use our package. And overall, if we look at the actual size of the estimates from these methods, both conventional KDEs and MCPs were smaller on average by a factor of 3. And the conventional KDE is the href. And the KDE with LSCV and the LOCO by a factor of sometimes 13. So they can, yeah, question?
No, sorry, you can finish.
Yeah, yeah, I think I finished, so it's good.
I had KDEs, at least the traditional KDEs, had this tendency to spill over the actual area that the animal uses. I was just wondering how you could use a KDE where you need hard boundaries for home ranges, or that's like an important aspect of what you're looking at.
Yeah, so if you have, what would you consider a hard boundary?
For example, either it could be features in the landscape.
Okay, so like an animal that doesn't go into water and you have...
One is that, or in
Yeah.
my case, like, for example, extremely animals which have very strong territorial behavior and have like really adjacent territories with literally like a line in between, and they do not, like they've been reported to not cross those sort of boundaries, and if you want to really test that, so how would, my understanding of KD is that you would have, the spillover effect is going to show overlaps where there may not be overlaps.
Yeah, I see. Yeah, because you would have essentially including an area that you know because of that boundary the animal would not use that area in any case. I think Chris might be the person to really answer this and how you would respond to that specific scenario.
Yeah, so if it's a known boundary, then that's really easy. You can do, at least now, we have RSF-informed KDEs, or you can have a shapefile for the boundaries. And then each kernel will be placed down that will respect those boundaries. If it's an unknown boundary, that's a little more complicated. And I would say with at least in your case, if you have the other the individuals on the other territory tracked, then potentially you could model that. You could model like repulsion from their density in an RSF. That would be a possibility, but it would be more complicated. You know, there is a trade-off between being predictive in areas that are accessible and spill over into areas that are inaccessible. That's just the thing with any of these non-parametric methods. And so the answer is, I mean, some people might tell you the answer is to just be respect all the boundaries, but then not be totally not predictive in the accessible areas. So have something that's just too small all around, and it's respecting the boundaries because it's too small. But the other answer would be just start going from non-parametric to parametric and start modeling the boundaries in one way or another. That would be the only way to get everything right.
And I think you also have to consider, especially if you're thinking of that territorial boundary, you'd have to be tracking all the individuals in that area. So if you miss one, you will be including areas of overlap that would not necessarily be right. Does that make sense? Yeah. So it's just a different question for the type of method that we are using. So another thing to consider about the AKDEs is that if you do have independent data, it does reduce to KDE and it will be essentially the same, except with a few bells and whistles to improve, increase confidence intervals or include confidence intervals and deal with some mitigation measures. So it's essentially the same in the case that you have independent data. So you don't need to switch to regular KDEs if you have independent data. You can still use our package, use CTMM. And yeah, like I mentioned, AKDEs in comparison with the previous methods, they do include confidence intervals. And this is very important for you to understand, how confident you are that your home range estimate is reasonable, right? So if you have wide confidence intervals, of course, it does include the potential true home range of the animal, but you do have that uncertainty that you can report and say it's between these values. And I think that's a very important information that you can get, and even for conservation implications and management decisions, you do want to make sure that you include that confidence that you get with your estimates. So obviously, the bigger your effective sample size, which is this value, those estimates are gonna, or the confidence intervals are gonna stick closer to the actual estimate. So that would be an ideal scenario, but obviously in the field, you're not necessarily gonna get that. So yeah, so we can see here that this confidence intervals for this particular individual, which has a effective sample size of around 7, are very, very wide. So it could be between 1,000 square kilometers or 1,600 square kilometers to almost 8,000 square kilometers. But again, that's because you don't have enough data to really get a good estimate. But this way, at least you know that. Yeah, and you saw already that if you plot home ranges with CTMM, you get these 395, and again, the middle one is the estimate, and the two others are the confidence intervals. So this is an example with real data from the African buffalo that we all are very, very familiar with at this point. And we have a really nice data set for this particular individual of over 5,000 locations. Unfortunately, the effective sample size is not the best, but it's not also the worst. 22 is still okay. And we can see here the difference that it makes for the previous methods as well. So the conventional KDE and the AKDE, and how that underestimates with KDE over the AKDE by over or almost 40%. So plenty of areas that the animal from this data set we know that would potentially use in the future that are not being quantified. And again, the same thing if we tried the thinning of the data that we mentioned before. But to achieve this for this particular data set, you'd have to remove over 99% of the data. Again, you end up with 35 locations. And if we plot the home range areas with this, we can see that obviously it approximates it better because, again, the KDE does have the assumption of independence. But again, you lost all that information. Why? And it's still in this case overestimates. So it's still not perfect.
I have a question.
Yep.
So earlier in your talk, you were talking about how the gold standard is really to get them from birth to death, because then you get all of that different information based on, I don't know, whatever life stage they're in or using different areas.
Yeah.
So if you have individuals where you have lots of annual home ranges, and some you maybe have just like 1, and others you have like 10 years, or some we even have 17 years of an individual. would you always want to go for the multi-annual home range and estimate that? Or is there any value in doing it annually? Because I feel like I can't compare the space use of these individuals if I'm using 1 year for one and the
Yeah.
other one has 5 years
Yeah.
of data, because I feel like that's apples and oranges or not like versus like. So what do you, like, if you're like just saying like, okay, for this one individual, this is really their home range. But if you want to kind of compare individuals, would you
Yeah,
still want to
'cause
go
you'd
with like
have-
1 year and 1 year?
You'd have different time frames that you're looking at, right?
Yeah.
Yeah, it's a bit more difficult because, again, you don't want to compare things that are not comparable. And if you have an animal with 2 years of data and you know that it does have that slight shift versus an animal with only 1 year of data, that you don't have the information yet for that, then you can't really compare the home ranges the same way. You could potentially do annual home ranges. We'd have to see how then that subset of data looks like. And if you have some guarantee that within that year, we know that the animal stays also within that area and doesn't go anywhere else. And then you potentially could compare. But yeah, it's case by case. You can't say it works every time or it doesn't work every time. But yeah, you could potentially do annual home ranges and then compare that way, as long as you have some guarantee that within that it stays before you do the shift.
Yeah, thanks.
Okay, so there are essentially 4 main mitigation measures that account for biases common in data sets. So 4 mitigation measures present in the CTMM package that we can do. This first one is default, so you actually don't need to worry too much about this. At current times, it is, if you run an AKDE, it's doing this AKDE-C, the area corrected. But I think it's important to at least understand that it is happening. And once you have an AKDE, it is doing this correction already in your data. And the main thing that it's doing is that typically for both conventional KDEs and the original AKDE, so not the AKDE-C, is that any sort of Gaussian reference function does tend to oversmooth a little bit. You can see that from the KDE href, right? It oversmooths the area versus LSEV, which tends to tightly conform with the points. So there's always a tendency for Gaussian reference functions to do this, which is what the original AKDE did, was that Gaussian reference function without this correction. So essentially what Chris did was basically correct for that. So you don't need to worry about this bias anymore. But just so you know that it is happening in the background once you calculate AKDEs. So this is what would be the difference between the AKDE without the correction and then the KDE, original conventional KDE. A lot of a lot of saying conventional KDE, so you know what I'm talking about here. The Gaussian reference function for both these cases. This is just the thinning of the data that we saw before. But yeah, so it's essentially, we'll just slightly correct that overestimation and condense the shape, estimating a little bit inwards versus outwards. But again, not something that you necessarily need to worry about if I need to apply this or not. It's the default. Just keep the default setting, don't change it. So this is what you could see without the correction, what would happen. So the AKDE without the correction, AKDE-C with the correction, and this would get worse and worse as we get smaller effective sample sizes. So you can see the overestimation of the home range starts by 5%, then to 11, then to 27 once we have like a small sample size here. But again, don't have to worry about that. It's already default. Then we have another mitigation measure. In this case, if you remember, I was talking about maximum likelihood and residual maximum likelihood. which are essentially two different ways of doing the model fit, the movement model process that we want. We want the best fit model for that. And Chris has created this perturbative hybrid residual. God, this is a lot of words. Residual maximum likelihoods, PHREML, AKDE, which is very hard to say, at least for me. But yeah, so this deals with the autocorrelation estimation bias of the previous model fit estimators. Because again, as we saw, the ML performs poorly at small sample sizes. The residual ML performs poorly at small effective sample sizes. So there is now new methods that actually are good for both small absolute and small effective sample sizes. So there are 3 different ones you can use within CTMM. 99% of the time, just use PHREML, which is both for small absolute and small effective. So this one would be the best way to do the model fit for most cases. And again, you don't have to worry too much about this. It is the default. So it's the one that's doing every time if you just run an AKDE function. But again, you can do potentially in certain conditions. I'm saying with a lot of caveats. You can apply the other ones or even the ML, the maximum likelihoods, to speed up your processing of the home range estimator. But again, the differences are not, of at least the processing, it's only if, like you have a really, really big data set of, hundreds of thousands of locations that you would see like a lot of effect of the difference there. But yeah, if you want to speed it up, then you can use maximum likelihood. So yeah, so the first one would be effective. The second one would be small absolute. This one is for both, so it will work for all of the situations that you have. So we can see here what happens if we use these different model fit estimators. And this is specifically the problem when we look at small sample sizes, because this will not affect you if you have large enough sample sizes. So this is just an example with a lowland tapir. It's an initial tracking data set that was for 19 months of fixes between 1 hour. But this is just 2 days of data, right? So again, remember, we're talking about very, very small sample sizes here. And we would see that both the maximum likelihoods and the residual maximum likelihoods are underestimating that model fit, right? Compared to the new fancy estimator. And we can see here again with simulation data instead of real data, the impact of starting with a certain tracking data set and either keeping the large absolute size but reducing it to a smaller effective sample size, so coarser data, and how ML would underestimate the home range, versus both small absolute and small effective sample size, so both reducing the duration of the data and coursing the frequency. And that would also underestimate the home range. But again, remember that the PHREML is the default of the current CTMM. So then we have a big problem that we see a lot in data sets, which is this unrepresentative sampling in time. So if you have duty cycling tags or acceleration informed sampling or device malfunction or habitat related signal loss if an animal goes into a roost site, a cave, or some place that it makes the loss of the signal possible, and you have gaps in your data, essentially any sort of temporal gaps in your data, which are very frequent in your sample size or your tracking data sets, or any shifting sampling schedules between individuals or between times of the year or whatever. So this specific mitigation measure, which is the weighted AKDE, can deal with that until a certain point, but in most cases it at least corrects the estimate that you get. This is not default, so you have to specifically set it to do weighted AKDE, because weighted AKDE can take longer to run, so we can't put it default because maybe people would complain that it takes too long and we don't like AKDEs anymore. Gotta start basic, and then if people do have issues, you can correct for this unrepresentative sampling in time. So the main thing that the weighted AKDE does is automatically upweights observations during undersample times, or optimally downweighting observations during oversample times. So it corrects a little bit for those differences. So we have here an example, again, with the African buffalo, our very good friend. So this is a specific individual that unfortunately had an irregular sampling schedule shift. Essentially changed from, on average, one fix every hour to one fix every 2 hours. Again, I'm sure we can find even more extreme examples of change, but you can already see just a small change, how it's going to affect the home range estimate. So this is the uniformly weighted, so the AKD without assigning any correction. And we can see the shape comparatively to the optimally weighted, so the weighted AKDE. And we can see that for these, so the red is the 2 hour shift. And we can see how it's essentially compressing that comparatively to the uniformly weight. Again, it just applies a correction, and you can have cases where it's more or less obvious what the correction is doing, but it's always, if you have this sampling changes, it's better to do it with weighted AKDE, so you have a better estimate at the end.
So yeah, if we have like planned sampling changes, like here, or like intended, then that's pretty easy to think of. But then there is, of course, like as you wrote, like there is, depending on habitat or light quality and so on, there is gaps, like there's just data gaps. So you said before, or Chris said before, like yeah, that the algorithm will deal with data gaps. So what's exactly the difference between having some data gaps and having irregular schemes? Like, it could be that, of course, for a certain time, the data gaps result in different sampling schemes.
So what is your question exactly?
Well, my question would be like, well, we may always have some data gaps. Does it make sense by default to include this weighted AKD to like account for these, or is the model also without the weighting flexible enough to account for these data gaps that result in some uneven sampling schemes?
I guess it depends on the scale of the gaps that you're working with, right? Because obviously, if like occasionally there's a missing data point, occasionally like it skips a few data points. I mean, overall, that was not going to make much difference in this correction. And if you try it, it's probably going to look very, very similar between the optimally weighted and the uniformly weighted. Obviously, at certain cases, then if you have bigger and bigger gaps in comparison to your data that you have, you're going to have bigger and bigger problems. And it might be the case that you have to kind of evaluate depending on your particular case. I wouldn't recommend to do normal AKDEs if you have very big problems with gaps, because again, you are missing some information regarding that. But yeah, it's hard to give you a specific rule of this much gap is sufficient. It's a bit more tricky to do that.
Sorry again. Is it possible to, well, how would you, so sorry, I would probably then fit both and then compare them, like, for example, like this. Is it also possible to use some tests to compare which one actually fits the data better?
I don't think there's currently any test that does that for this particular difference here, yeah. Maybe Chris will, if you pass to Chris.
I think it'll help in both cases to have the weights, but in the case where the weights are scheduled or missing at random without being caused by, say, habitat changes, then it will work pretty much perfectly for what it's supposed to do. But if it's due to the habitat, then it will help, but it won't be a full solution necessarily, depending on the scales of movement, how they compare to the scales of the habitat that blocks the signal. In some regimes, it will be pretty much a perfect solution, and in others, less perfect. But it is fixing things in the right direction. It's just not necessarily a full fix for that problem.
And again, the main limitation of weighted AKDE is that will take longer, right? So if you're willing to wait for it to finish running, you'll always have a better estimate at the end. So unless it's if you, like, I don't know, it collapses on itself once you start running it, so something like that, that really makes it difficult for you to add this mitigation measure. But it should apply in most case scenarios. Okay, so the final mitigation measure is parametric bootstrap. And this would be if you have very, very low effective sample sizes. Like we're talking less than, let's say, 4, like if you have 2 or 3 or 4, depending on the situation. So very, very low effective sample size. This is something that you can apply in those certain conditions to really have a better approximation of the estimate. However, it is very, very, very time consuming in certain scenarios. So it's obviously you have to consider that if you have small effective sample sizes. But essentially, it just, you are assuming that the data comes from, essentially, there's a true distribution and non-distribution, and you have a sample of that true population. And we're just, essentially the parametric bootstrapping is just going to keep resample it until it gets a better representation of the sampling distribution. So obviously, because it is resampling this over and over again, it does have a very high computational cost. So something that could take 1 minute to run with a regular AKDE, if you do bootstrapping, it can be hours, if not days or more. Yeah.
Will there be like a warning or a hint that our effective that our effective sample size is that low that we should probably switch to?
You'll run the regular AKDE. You'll see that the effective sample size is small, and then you can potentially rerun it and apply. I mean, it's not doing that automatically. It's not a default setting or anything. You'll see we'll go through an example of that just to see what happens if you have small effective sample size. And once you have that, then you have to apply the bootstrapping to it. But yeah, just be aware that it will be very, very time consuming. Most likely to just have your computer running for a while in the background. Yeah, so we can see here just a general comparison between these, starting from essentially the conventional KDE, the initial AKDE without the area corrected mitigation measure, the area corrected AKDE, the PHREML AKDE, the PHREML weighted AKDE, and then bootstrapped. I'm not going to say the other words, but you essentially going further and further in complexity of the mitigation measures. And we can see that the AKDE without the area correction did tend to overestimate at certain sampling durations. but then it converges to the truth at longer durations. But again, you don't have to worry about that. The AKD-EC is the default, so we would eventually converge and have only the underestimation of it. If you do the PHRE-ABEL, it would improve even more the relative area of the relative error of your estimates, and then bootstrapping as well. But again, we only ran it for I think up to 4 days, because again at that point it does take a long time to run. So it's not necessarily needed at that point, because again it's only for effective small sample sizes. So that would be the best to actually achieve lower relative error, but again it doesn't need to apply in most conditions, because as you can see, for longer sampling durations it will eventually converge to the truth for even the other methods without going too deep into the mitigation measures. But yeah, so you can see here the computational time of bootstrapping. It just keeps going. So at one point you'll have problems with this if you are doing your bootstrapping as a mitigation measure. Okay, so let's actually go over the codes.